Okay, so today I'm covering 4.6, which is graphs of other trigonometric functions. Um, this is not going to necessarily be helpful for the assignment, but it is very helpful for moving on to calculus because you do end up with different types of trig functions and their graphs, and understanding how to graph them so that you can figure out things like derivatives is very helpful. So this is more of a, this will be helpful for you in future courses versus maybe not necessarily be helpful right now. Okay, so we're going to just go through all the different types of trig functions, and while I encourage you to sketch them or to basically use Desmos to graph them, I'm also going to show you how you can determine things like where the asymptotes are, the period, the domain, and then figure out, what it kind of looks like by hand, just so you have a better understanding of it, especially because it's really difficult to view these when you're graphing in Desmos, because Desmos doesn't default to having the x-axis as radians. It can graph in radians, but it won't label them as like pi or 2 pi or those sort of things. So you have to do some manipulation, and it's just a little harder to follow if you look at it in Desmos versus like graphing it by hand. So I'm going to be doing these by hand just to show you kind of how everything works and how you can determine the different properties, but you're welcome to use Desmos to actually graph. And in fact, I often do that to verify that my graphs are correct as well. So starting with tangent. Tangent is an odd function, so that means when you plug in a negative value, it's negative output, and that makes it symmetric with respect to the origin. So that's how we get these things that look sort of like cubic functions but are not actually cubic functions. So that's how we get the basic shape of the tangent. So the way tangent is, because tangent is sine over cosine, there are asymptotes wherever your cosine of x is equal to 0. So there are asymptotes that we need to worry about. And so you can find those by taking whatever you're taking the tangent of, the inside part, setting it equal to plus or minus pi over 2, and then that will give you the location of two asymptotes. And then once you know that, you can figure out the period, and then that will tell you when those things are repeating. So knowing the asymptotes and then the period help you determine what your graph is going to look like, and then you can fill in the gaps in there. So those are the two most important things that I usually focus on. So for tangent, unlike sine and cosine, the period is pi. Sine and cosine have a period of 2 pi. Tangent, the period is pi. So it's basically half the period of with the trig functions we've been working with so far. And so you can see that our asymptotes are basically, they start at pi over 2 and negative pi over 2, and then because of the period, you add pi to that to get to the next asymptote. So that's why they write the vertical asymptotes as pi over 2 plus n times pi. It just means you keep adding, or you could subtract pi if n is a negative number, and then that's going to give you your next asymptote, so that there's a pattern. So every asymptote is separated by the period. So those are the most important things for graphing. So let's just get to it. So for all of these, I have put in the base of what it looks like, so you have something to kind of guide you while you're graphing this. So for our first example, we want to sketch y equals negative 1/2 tangent of x. So negative 1/2 here, this is a vertical stretch, and actually it's going to be a shrink in this case because it's 1/2. And because it's negative, we have a reflection. So that is really important, so that we know that what our graph is normally for tangent is going to be reflected, so it's going to be upside down. But the nice thing is, because it's just tangent of x, we have no changes to the period, to the asymptotes. We're not changing any of that stuff. So we are basically taking our existing graph that I have here, and then we are going to shrink it down and reflect it upside down. So I'm going to just make a sketch. Pretend these are straight lines. And so these are sketching, so it's not going to be, you know, perfect, but we're going to label the same labels that we have in our base graph. So we're just going to count everything by pi over 2. And then just label 1. Let me space these out a little bit. Okay, so that's good enough. So our asymptotes are unchanged because we haven't done anything inside the tangent function. It's still tangent of x. So I'm going to draw my asymptotes. Okay, so I've got those all changed, or all those graphed. And now I'm going to put in our x-intercepts. Those are not changed because we didn't shift left or right. We didn't shift up and down. So our x-intercepts are going to stay the same. So my center points are going to be the same. And now I'm going to just kind of eyeball things. So if you notice, about halfway between our 0, 0 and pi over 2 on the tangent here, it crosses at about 1. So that looks like it's a, you know, we've got a point there. So I'm going to, again, take halfway. If I'm crossing at 1, I'm now multiplying that by -1/2. So this point that I've labeled is approximately pi over 4, because that's halfway between 0 and pi over 2. And it looks like the y value is 1. So because we have that -1/2, that happens to the y value. So now we're going to have pi over 4, and then you're going to multiply 1 by -1/2, and I'm going to use that as a value to kind of graph. So at about pi over 4, I'm going to be at about -1/2. And so that's where my reflection comes in. And then because it is symmetric, I can finish that for the other side. So you can see that we have a reflection upside down, and then we shrank it down so it's a little flatter in the middle than it would have been normally. Now this is not to scale, so that's why this is a sketch, because my scaling here is really bad. But you're going to use the same sort of principle to fill in the other points. So if it was to scale, you'd see that it would be it's a shrinking it much better than it is, than you can see in my really bad sketch. But that's why this is a sketch, because it doesn't have to be perfect, but it's good enough to give you the general shape. So that's how you can sketch something like this, where the only transformation you have occur is a vertical shrink and a reflection. Do you have any questions? How do you know where to sketch the vertical asymptotes? Is it always the same? That is an excellent question. So that will be the next example. Our asymptotes are going to be different. And why that is because of what you have here. If it's tangent of x and you don't have anything happening to that x, so you're not having anything else happening in tangent, it's just x, your asymptotes are going to be the same. But if you have something multiplied by x, if it's like 2x or 3x, or maybe it's x plus 5 inside the tangent, that's when the vertical asymptotes are changing. Because anything that you do to x changes the vertical asymptote. So anything that happens inside the tangent function changes the vertical asymptote. So if I move on to my next example here, if I can find my mouse, here we have pi x. So now that means our vertical asymptotes are going to be changed because we're multiplying the x by a number. And so that's going to change the location of the vertical So the number in front, that is just like the -1/2. This is just going to affect the y value, and this is going to be a vertical stretch. And then this pi x, because we have the pi, this is going to do stuff to x. And it's kind of hard to describe what it does, so I usually just note that the pi affects the asymptotes, the period, and the domain, because all of those are based off of x values. So anything that's based off of an x value, so of course it affects the x-intercepts as well. But that is mostly affected if you're adding or subtracting things to x. In this case, our x-intercepts are going to be roughly the same. What's going to happen is that they're going to be labeled differently. So going back, the key that we're going to be doing here is that we're going to start by finding the asymptotes, and we are solving this equation for when we have tangent, where you can see that bx minus c, that's whatever's inside the tangent. So you set that equal to where the initial asymptotes are, pi/2 and -pi/2. And then when you solve for x, that will tell you where the new asymptotes are. So we're going to start with that. So I'm going to start with our vertical asymptote here. So it's bx minus c equals ± pi/2, and that's specifically for tangent. So the inside of our tangent function is just pi x. So I'm going to say pi x is equal to ± pi/2. So we're going to solve for x, and we do that by dividing both sides by pi. So divide both sides by pi, and those are going to cancel out, and we're going to end up with ± 1/2. So x is now ± 1/2. So now our vertical asymptotes have changed. They're not at pi/2 anymore. Now they're at 1/2. The next step is to find the period, because that is also important. So our period is essentially, they don't actually give you a formula, but it's the period of, in this case, tangent divided by b. So if you remember back, or if you've looked at the stuff for sine and cosine, the period is 2 pi for both of those. And then when there's shifts or things that happen to x, it's 2 pi divided by b. Because the period of tangent is pi, in this case it's pi divided by b. So our new period is pi, because that's the period that we're given here for tangent. And then b is the number in front of x. So so b is this number here. So we're going to be dividing by pi. And this gives us a new period of 1. So what this does is this tells us where our next asymptotes are. So your asymptotes are basically, they're going to be based off of here, our domain. So I'm going to say our domain is all x except, so we can say not equal to 1/2 plus 1 times n. So you basically add 1 or subtract 1. If n is negative, then you're subtracting 1. And that's how you determine where the next asymptotes are. It's the period. So even the asymptotes repeat with that period. So the first thing that you're starting here, this is the asymptote. You start at one of the asymptotes, and then you add on the period of the function, and that's how you determine the domain. So we're going to start at 1/2, and then we're going to add 1, and now we're going to be at 3/2. Then the next asymptote, you add 1 again. That's at 5/2, and so that's the pattern. So once I figured out my vertical asymptotes, my period, and my domain, if there's no horizontal or vertical shifts, I can start getting my, so I'm going to draw my axis. And then instead of labeling them with pi over 2, I'm going to make it easy for myself, and I'm going to label it with 1/2 and count by 1/2 because the vertical asymptotes are at 1/2. So it just makes it easier if I don't bother counting with pi's or anything like that, because it'd be really hard to kind of approximate where that is. Whoops. But even though my hand wants to write a pi there. So because it's a sketch, it's just easy enough to relabel things. I'm going to use the same vertical axis. So once I've decided on my labels, I'm going to draw on the vertical asymptotes. So those are going to be a plus or minus 1/2. So you can see that it's roughly the same shape as our other one. And then they're adding, they repeat every one. So I don't have the one labeled on the left, I gotta draw it. So I've labeled my asymptotes. Now, because we did not shift left or right, we didn't have anything added to x, so we don't have anything moving left or right. The center for all of these is going to stay the same as it does in the picture, basically. So it's basically going to be half, in the middle between the two asymptotes. We don't have a reflection because we don't have a negative in front, so the shape is going to be the same. The key is going to be, well, what are our new points? So again, I'm going to do what I did before. So we had about pi over 4, and then that y value appears to be 1 based off of the graph. But if we want to kind of look at our new shape, now it's going to be halfway between 0 and 1/2. So now it's going to be a 1/4, because that's about the halfway point. And then because we have a vertical stretch of 3, we're multiplying the y value of 3. So that's going to be a 1/4 3. So that kind of gives me an idea. And a vertical stretch makes your thing narrow. So the shape is going to be the same. And so you can see that this actually makes it much narrower because of that vertical stretch. So then I'm going to keep the pattern going. And it's a sketch, so it's not perfect. And so let's see, I'm just going to eyeball here on the left. So it has the same general shape as tangent, but what has happened is that the asymptotes are new locations, the period is different, and it's been stretched upwards. But it looks essentially the same because what we did is instead of trying to draw it on the same exact scale, we've adjusted the scale to make it easier to graph. Do you have any questions? Okay. So next one that I have here is going to involve a shift left or right so that you can see what happens with that. So in this case, I didn't have a number in front, so we don't have to worry about any stretches or anything. We're just going to look at what happens when you have a shift left or right. So we have y equals tangent, and then inside we have x plus pi. So that x plus pi thing, everything inside here, once you have something happening inside there, that's going to be affecting your x. Because we have a plus pi, we have something added on, that's a horizontal shift. So we're going to be shifting left or right. And then just as a note that this is affecting, because it happens to x, it's affecting the asymptotes, the period, and then the domain. Although in this case, I'm going to put period in parentheses because that is mainly if your coefficient if b is not equal to 1. So if there's a number in front of x, then that affects the period. In this case, the number in front of x is 1, so our period is not going to end up being affected, but in general, anything that happens inside there affects the period. So I'm going to start with finding my asymptotes. So I always just write the form that the asymptotes come in so that I remember it's whatever's inside the tangent is equal to plus or minus pi. So we have x plus pi equals, I said plus or minus pi, I meant plus or minus pi over 2. So x plus pi is equal to plus or minus pi over 2. And then we're going to solve for x. So you would subtract pi from both sides. And I'm going to put that first so that it's negative pi plus or minus pi over 2. So this is going to kind of help me figure out where my asymptotes are going to be. So I figured out my asymptotes, and I'm going to just put those in right now. Because we have a plus or minus pi over 2, I'm going to just start counting by pi over 2 again. And so we've got where our asymptotes are going to be. So the first one, so we have negative pi plus or minus pi over 2. So it's negative pi plus pi over 2, which gives you negative pi over 2. So you can see that it actually ends up in the same spot that we had before. And then if we do negative pi minus pi over 2, that's going to give us negative 3 pi over 2. So I'm going to pretend that I labeled that, and that would be right over here. So we've got two asymptotes labeled based off of what we've solved here. Got those in. Next would be the period. So our period is just the period of tangent divided by b. So the period of tangent is pi, so this is going to be pi over b. And b in this case is 1 because we don't have a number in front of x. So our period is still pi. So there's a difference of pi between each of our asymptotes. And you can confirm that based off of when we solved that we had negative pi plus or minus. So the difference between those is pi. So that same distance is going to be between the next asymptote. So you can use that to complete your picture. And you can see that the asymptotes have landed in the same exact position that we had before. So we added pi, but because the period of tangent is pi, it doesn't change anything. It's still going to look like tangent because we just basically added the period and it's just moving over, but it's moving over the same amount as what it looks like. So it doesn't actually end up looking any different. So I'm not going to bother with the domain because we've pretty much established it's going to look exactly the same. And so I'm going to fill in my 0 points, and then I'm just going to kind of estimate or roughly fill in my graph as best as I can. So we end up with the same exact graph, tangent x. Because all we did was add the period, and because of the fact that it does repeat, that doesn't do anything. Are there any questions? Okay. So next is cotangent. So cotangent is the reciprocal of tangent. So basically it sort of looks like a reflection of tangent. So it has the same basic shape, but it's a sort of a reflection, but also note that the asymptotes are in different locations. So the shape looks like a reflection, but it also is sort of shifted over because tangent started at 0, 0. Cotangent is shifted to the right because we actually have an asymptote at 0, but they don't really draw that in so you can see that better. So it's like tangent shifted over and reflected to get cotangent. So the period is the same, but the domain is different. Where the vertical asymptotes are different. So the way that you create your graph here is a little different. But we're still going to use the same basic ideas where we're going to take bx minus c and we're going to set it equal to the asymptotes. And so one asymptote is at 0 and then the other one is at pi. And that will give us the location of two asymptotes, which then we can use to do the rest of our graph. So I'm starting off with y equals 3 times cotangent of pi x over 2. So I just like to write down what everything does. So that 3, that's going to give us a vertical stretch. So that's going to be multiplying y values by 3. And again, I'm going to be kind of using values on my existing graph where the y value is 1 to kind of help eyeball where that's going to be. And then we have pi x over 2. And so because we have a number multiplied by x, this is going to be affecting the period. And then it's also affecting the domain and the asymptotes because things are happening to x. So I just like to write that down so that I remember everything that I have to think about. So I always start with the asymptotes. And for cotangent, you have bx minus c equals 0 and bx minus c equals pi. You don't have to choose those two if you don't want to. If you wanted to pick two other asymptotes on the graph, like you can see there's an asymptote at 2 pi. If you wanted to use 2 pi and pi instead, that's fine. You just need to basically pick two of the existing asymptotes to cotangent, and then you're going to solve. So inside our cotangent, we have pi x over 2. So we're going to set that equal to each of our asymptotes and then solve for x. So for pi x over 2, if I multiply both sides by 2, I'm just multiplying by 0 on the right. It's still going to be 0. Divide by pi. So we're going to get x equals 0. That doesn't do anything. Anything times to get 0, something has to be 0 there. So x is going to be 0. Now on the right, if I multiply both sides by 2 over pi, multiplying by the reciprocal, 2 over pi, you can see that the pi's will cancel, and so we're left with x equals 2. So now our asymptotes are going to be at 0 and 2. So once we've gotten that, I'm going to go find the period. And so the period is always the existing period of your function divided by b. So our period here, just like with tangent, it's pi. So it's going to be pi over b. And b is what's in front of the x, so that's going to be pi over 2. So we have pi divided by pi over 2. So that's the same as doing pi times 2 over pi, and we end up with a period of 2. So that means our asymptotes are going to repeat every 2. So that will help us fill in the rest of the graph. And then just for good measure to indicate the domain, it's going to be all x, where x is not equal to, I'm going to start with one of my asymptotes, which in this case is 0, so I could just have 0 plus our period, which is 2 times n. Or you can just say x is not equal to 2n. So it's pick one of your asymptotes, and then you add your period times n to figure out the domain. So once I've labeled those, I'm going to draw. And because my asymptotes are at 0 and 2, I'm going to just count by ones. I could count by twos if I wanted to, but you want to count some way that makes it a little easy for you. And then 1, 2, 3, -2. I'm really bad at making these drawn at least approximately to scale. So I'm just counting by ones, and so I'm going to start my asymptotes. So I know I have one at 0, so I'm going to draw that in. And again at 2. And then that means, because it's a difference of 2, I also have one at -2. So in between each of the asymptotes, we didn't shift up or down, so we're going to be starting in between halfway. So I'm going to put in all of those 0 points. I don't have a reflection, so the shape's going to be the same. And we're going to look at our key point here again. So it looks like what I had put on my graph here is about at -π/4 and 1. So now we're kind of shift over. I don't really care too much about where that actual x location is. What I care about is the fact that I'm multiplying that y value by 3. So that's now going to be at a y value of 3. So I've got my, oh, I labeled that as -π/4. That's actually regular π/4 because this is 0. Put 0, 0 on the graph. Getting a little confused there. So I'm just going to make sure I have the same shape, and I'm going to make it go up to 3 instead, because we're multiplying it by 3, which then means it goes down to -3 in the other direction. So I'm just going to estimate halfway between these, and then draw my pictures. And I need to make sure that I have the same shape, and then that's going to be up here. So it has the same shape, but what changed was the location of the asymptotes and the period. So it's actually a different period and asymptotes. Now the y values it's been stretched out a bit. Any questions? Okay. So next one here, we're going to have a shift. And this shift is actually going to be a different shift from the period. So it's actually going to sort of be more, it's going to look different compared to when we had our shift with tangent. So I have y equals 2 cotangent, so that's going to be 2. So we have a vertical stretch of 2. So that means instead of going up to 1 on my graph, I'm going to make it go up to 2, kind of as a eyeball point. And then we have this x plus π/2. So the period here is going to be unaffected because the value in front of x is 1. So period is unchanged because b is equal to 1. The number, whatever's in front of x, is 1. However, because we added something, what's going to change is the domain and the asymptotes. Oops. And that is because we have something added and subtracted. So domain and asymptotes always change no matter what is, if there's something done to x, it's just the period that sometimes does not change. So as usual, I'm going to start with my asymptotes. And it's going to be bx minus c equals 0. and bx minus c equals pi, because those are the existing asymptotes on our graph. And bx minus c is what's inside the cotangent. So this is going to be x plus 1/2 equals 0, x plus 1/2 equals pi. And then you're going to solve each of those for x. So the first one, we just subtract pi over 2. We get x is equal to negative pi over 2. The second one, if you're subtracting pi over 2 from pi, you're going to be left with another pi over 2. So that's going to be pi over 2. So I'm going to just draw my asymptotes. And because these are at pi over 2, I'm going to just count by pi over 2. So you can see that already the asymptotes have shifted because they originally were at 0 and pi, and now they're going to be the same asymptotes that we have for tangent because they've been shifted over. So our asymptotes have changed, and I can kind of eyeball where the next ones would be here, roughly. So I've got those asymptotes in. I've already said that the period is unchanged, so the period is still going to be 1, or still going to be pi. So the period is unchanged, it's going to be pi. So this means that our domain in this case, we start with one of the asymptotes. We usually start with the positive asymptote. So positive asymptote that we found was pi over 2, and then we add on the period times n. So it'd be pi times n as our new value to find the domain. So next step is actually to plot my 0 points. So I need to plot them in between each of the asymptotes. The shape is unchanged, but now I have a vertical stretch. So instead of going up to 1, I'm going to go up to 2 and negative 2 when I estimate my points. And so I have to remember that the shape is going to be the same. And so I have to kind of put my estimates in. And then I just follow the pattern. And there we go. So the biggest difference here is that everything has been shifted over by roughly pi over 2. Because with cotangent, it was originally one of the center points was at pi over 2. I get my highlight out so we can see that we had a center at pi over 2, but now that center has been moved over, and now it's at 0. So it was shifted over by pi over 2. So because we added pi over 2, you can think of that as a negative shift, a shift left, but it doesn't really matter because of the fact that this just keeps repeating. So it doesn't matter whether you say it's shifted left or right, it's going to look exactly the same, but it moved over by pi over 2. Any questions on this one? Okay, so now we're going to move on to the difficult ones. I don't mind doing tangent and cotangent by hand because they're not too bad, but secant and cosecant are kind of a mess. And so these are usually the ones that I rely on using technology for the most because they are harder to determine where your thing needs to go. And I have a tendency to go backwards and shift things to the left when they should go right and kind of get things in reverse. So these are difficult. So the key about secant and cosecant is that they are basically reciprocals of sine and cosine. So the period is the same as sine and cosine. So the period for both is 2 pi. But there are asymptotes because you end up dividing by 0. So we do have asymptotes, and so you end up with like U-shaped things, and I'm going to color over these so you can see them a little better. So you end up, secant and cosecant give you U-shaped graphs. And the reason why they show sine and cosine on these graphs is because when you graph these, it's a lot easier to graph them if you graph sine and cosine first and then make the u's going from there. So that's sort of the easiest way to graph it. So that's generally how it's taught, is that to first graph sine or cosine and then make a u kind of where the peaks are. And that will give you your secant and your cosecant. You can also do it without doing that. So like I'm going to show you how just to use the transformations basically in my first example, but then from there I'm going to show you how to do it with the sine and the cosine stuff, because that's where it gets tricky. So first example, sketch y equals 1/4 secant of x. So this is easy enough to do just by shifts or using the rules of transformations, because the only thing that's changed here is that 1/4. And so this is just changing our y values. So normally our little peaks are at 1. Now they're going to be at 1/4 because they're going to be multiplying them by that number in front. So here it's at -1, it's going to move to -1/4. But nothing else has changed. It's still secant of x. So this is easy enough to just understand that fact and graph it. So I can use all this space. Nothing's changing on the x, so I can label those the same. And then I have 1, 2, -1, -2. So I'm going to start by, none of the asymptotes are changing because we didn't do anything to x, so those are all going to be the same. And the tricky part thing, what I figure or think of as tricky with the period is that because of the asymptotes, you're inclined to say the period is pi, but it's 2 pi because it kind of alternates where the u is going with each one. So that gets a little tricky. So generally these u's start at 1, but because of that 1/4, I'm now going to start them at 1/4. So I put it at 1/4. I have a key point here, 0, 1, but my transformation is now going to make that 0, 1/4. And then I'm going to just draw my u. And then the next u's on either side are going to be in the opposite direction. So I can graph those. I put those in going down. And then if I wanted to continue the pattern, I can then make the next u going up. So that's what secant looks like, especially if you don't have the sine cosine stuff in there messing with you. It's just basically u's. They look like little mini parabolas, basically. They're not exactly parabolas, but they look like parabolas that repeat and kind of alternate going up and down, if that makes sense. Are there any questions? Okay. So now I've got another one here, secant. We have y equals -2 times the secant of 4x. Now, if there's no parentheses, it is assumed that that +2 is not with the secant. So if there's no parentheses, that +2 is outside of it. So that's secant of 4x plus 2. So to kind of break this down, we have this -2 here. So we're going to have a reflection, and we're going to be stretching by 2. So those y values, the key points of like where a y value of 1 is now essentially going to be multiplied by -2. Then we have this +2, and that is going to be adding to y. These two reflections, or these two transformations, go hand in hand. So on our graph, I have 0, 1 on the original secant graph. The first thing we do is the multiplication, so that will transform it to 0, -2, because you're going to multiply your y value by -2 since that's what's in front. And then we're going to do the shift where we're adding 2, so that gives us 0, 0 as our new reflection point, or our new point. Reflection is not the good word, transformation point, or the new starting point. So you do your multiplication of y first and then your addition. Now we need to also do this with another point here. So I'm going to pick, we have another point on the original graph, which is 0, not 0, it's at pi -1. So I start by reflecting, or by multiplying that y value by -2 because of the reflection and stretch. So that gives us pi 2, because -1 times -2 is a +2. And then we do the addition of 4. So that, nope, not 0. I keep wanting to write 0, pi 4. So we're going to keep those in mind. Those are those 2 points that I have labeled on the original graph. We did the -2 in front, and then we added 2. So those are, we're just going to keep those in mind because those are going to kind of help us determine where our y values are. So next I'm going to take a look at the asymptotes, and that's going to be changing because of the 4 times the x. So just like tangent and cotangent, multiplying that x by a number changes your asymptotes. It's going to change your period. It's going to change your domain. So all of those are going to be changed. So I'm going to start with the asymptotes. So note that our original asymptotes here start at pi/2. So we basically, it's the same process we've been doing. We basically have the plus pi/2 and the minus pi/2 that we had with tangents. So I'm going to just take that 4x that's in parentheses, and I'm going to set it equal to plus or minus pi/2, because those are the two asymptotes that I have existing on my graph. They're easy to work with there. So I'm going to solve for x, so I'm going to divide both sides by 4. And so that will actually give me pi/8, because that's the same as multiplying by 1/4. So now my asymptotes are going to be at plus or minus pi/8. Next is the period. So to find our period, we take the existing period of our function. So secant, it's 2 pi, and then we divide it by b. So it's going to be 2 pi divided by b, which b in this case is 4, because that's the number in front of the x. So that gives us a period of pi/2. So here's where we start getting into some tricky stuff, and this is why these kind of functions with the secant and all that are very tricky to kind of graph. So I'm going to not worry about the domain for now. I'm just going to start with kind of giving you a graph. So since my asymptotes are at pi/8, I'm going to use that. I'm going to count by pi/8. So that would be 2 pi/8, which is pi/4, 3 pi/8, 4 pi/8 would be pi/2. And then I'm going to do the same thing in the other direction. Okay, so now I'm going to just draw in my asymptotes. So they're at plus or minus pi/8. Now the nice thing about the way that we have all of the way that we label everything is that basically your asymptote is going to be every other thing that you've labeled as long as you were counting the same. So I can draw the rest of those in. So I've drawn in, this is not to scale, because I can definitely see my shapes are not equal, not to scale. Okay, so now this is the tricky part where you're trying to figure out kind of where your center part things are going. So this is the part that I always mess up, is trying to figure out, well, am I going to be starting up, or am I going to be starting down? That's the big question, is where do I start? Is it going to be an up or is it going to be a down? So we're going to go back to our rules of, wait a minute. Nope, not the rules of transformations. This is where we're going to go back to kind of thinking about what secant is. And this is where they suggest that you actually graph your cosine or your sine first. So, oops, I don't want the highlighter. And I want to go back to black. So secant is equal to 1 over cosine. So let's pretend that we are looking at -2 times cosine of 4x plus 2. So this is how they kind of decide that, or kind of help you graph and figure out where this is going to be. So we've already found the period, 2 pi over b. We need to find how things are shifted over. So this is what we're, oops. The shift is the important part, if there is a shift. And we do sort of have a shift here. So our rules for sine and cosine is that when you have a cosine or a sine, your shift is basically, it's going to be c over b as one value, and then c over b plus your period. So we don't have a c value. It's going to be 0, but b is going to be 4. So we're going to be centered at 0 for our x. So, well, we knew that already. So I'm going to just kind of put that there. Then we add our period. So our period here is pi over 2. So next at pi over 2, I'm also going to be at 0, which means at this pi over 4, I need to be at my other value. So if you're wondering, this 0 thing that kind of is that I'm, so this is 0, oops. I want the highlighter. This 0 is corresponding with this 0 that we had done all the way at the beginning there. And then that's telling us where these locations are. So this is telling us, okay, they're going to be repeating. So that means in between these, I'm going to be at the 4 part, the other value that we have there, this 4. So at my pi over 4, I'm going to, let's just say this is 4, -4 there. So at pi over 4, I don't have any dots, so that's going to be at 4. And then this one is also going to be at 4. So because of the general shape, the lower number is going to go down, and then the higher point is going to go up. So this allows me to sort of finish or get the basic shape there, which means that this one is then going down. So this is why I say that secant and cosecant are kind of confusing, because you have to kind of think about, okay, what does the reciprocal look like? Where would be? And then you have to fill in the blanks there. So I had to figure out where those lower points, the zeros, are. Then that allowed me to figure out which ones were the high points. And this is what we come up with. So we've got 5 minutes basically left, and I do have a few more examples, but not enough time to go through those. So it's fine if you do like the cosecant ones. Basically, they're just shifted over, but it's the same sort of thought process. So I have 2 additional ones that I haven't gotten to, but it's the same sort of thought process, and you can verify this in Desmos. You can graph them in Desmos perfectly fine, and that is probably the best thing to do with secant and cosecant, just because they are really difficult to think through. You can see that even me, as I'm trying to think through this and logically think through it, it gets kind of confusing. So hopefully this helped you at least have an understanding of how these work. Cotangent and tangent are going to be the most important ones that you really need to know anyway, especially when you go to calculus. So I would worry more about those and less about the other things. So I'm going to skip these, and this is just my final slide here, just to talk a little bit about damped trig graphs, because damping is actually something that you see when you get into electric circuits. So you'll have things that are damped. And basically what that means is that you have a trig function and you're multiplying it by a value. So this graph is like x times sine of x, but sometimes you'll see e to the x times cosine x, or e to the negative x times tangent x. You're usually multiplying your trig function by another function that's not a trig function. And there's various different shapes to them. Usually what happens is that the middle around the origin kind of gets smaller, and then they get bigger as they grow. But it depends. Sometimes they can do the opposite. It all depends on basically what the functions are that you're multiplying it by. But it's just something to kind of understand and to know the terminology, so that when you see these, when you go into, say, electrical engineering kind of classes where they talk about damping, you have some understanding of what that means. So that's it. Thank you for bearing with me. Hopefully that secant graph wasn't too confusing. It's just something that is probably easier to use technology, but I wanted to go through at least some examples, as many as I had time for, basically to show you how you can do it by hand, but it is a little confusing. So I will talk to you guys later, and I hope you guys are having a great night. Thank you for attending, and bye.